Hey guys, welcome to the level 2 waves topic test walkthrough for the topic test we just did about 2 or 3 days ago. So this will be the walkthrough for question 1 and 2. So question 1, okay, says John is having a day at the local theme park. He likes the Motion Master, a hydraulic moving theater which he watches a screen and the seat that he is sitting on moves. The screen is 6 meters away from the projector and the height of the image on the screen is 3.45 meters. The size of the film passing through the camera is 36 millimeters. A. State the type of lens that will be required inside the projector to produce a real image on the screen. So you know that the only type of lens that can actually produce the real image is the convex mirror. A concave mirror can't actually produce a real image. So your answer here will just simply be the convex lens. Because the concave lens cannot produce a real image, it only produce a virtual image. So if you just state the convex lens here, that's just an achieve question there. You get 1 achieve point. So B, calculate the magnification of the image. Alright, so now first thing we're going to do is to note down what we know as our variables, okay? So we note that the screen is 6 meters away from the projector. So sorry, I forgot to label this. So the right side here, that's the screen. And the screen is 6 meters away. So the screen is 6 meters away from the projector. And the image is actually displayed on the screen. So therefore you can say that the distance of the image to the lens is 6 meters. Okay, and that's because the only reason that's because is because the image is projected on the screen. Because the image is projected on the screen, that means the image is in the same place as the screen. So therefore the distance of the image to the screen to the projector is 6 meters. So we're gonna note down, okay, that our DI, we'll note down our DI equals to 6 meters. Actually, we're gonna change everything to centimeters, okay, to make it a bit easier. But you don't have to do this, but it's just easier on. I just prefer the centimeters. So our second variable, so the height of the image on the screen is 3.45 meters. So we can note down that the height of the image, so HI is HI we can note down is 345 centimeters. And we need one more variable, so that's the size of the film passing through the camera is 36 millimeters. So there's the size of the film and it's passing through the lens. That basically tells you that's the object. So the height of the object, so HO is 36 millimeters. So 36 millimeters converts to 3.6 centimeters. So we're going to label that our height of the object is 3.6 centimeters. Alright, so now we're going to go back. So now we have our variables written down. We're going to go back to our equations for the magnification. So you know that magnification equals to di over do, or is equal to hi over ho. So you know, as you can see, you have the hi and you have the ho, so therefore you can work out your magnification. So your magnification would be 345 over 3.6. And that answer should come out to be, the answer comes out to be 95.83. And that should be your answer for the magnification of the image, and that is a merit question there. Let's get us a merit point there. Alright, calculate the focal length of the lens. Okay, so once again, we're going to note down what the variables we know. So once again, we're just going to take it down. So we can say that DI equals to 600 centimeters. HI equals to 345 centimeters. HO equals to 3.6 centimeters. And we also know from the last calculation that magnification equals to 95.83. So now we need to find the focal length of the lens, okay? So notice that we need to find our equation for the focal length. So 1 over f equals to 1 over do plus 1 over di. Okay, but the problem is you only have di right now, but you don't have the do. However, you can use the relationship with di and magnification to figure out what do is. So you can come back to your magnification equation. So magnification equals to di over do. So therefore, you have your magnification. So 95.83 is equal to di 600 over do we don't know. So if we move the do to other side, so that just becomes 95.83 do equals to 600. Therefore, your do should come out to be 6.26 centimeters as your answer. So now that we have our do, we can substitute back into our focal length equation, and we can find what our focal length of the lens is. So now we can say that 1 over f equals to 1 over dO, which is we just found is 6.26 plus 1 over our di. Our di we found is 600. And that means we should find our answer should be, our focal length should be come out to be about 6.2 centimeters there. If you're not sure how to get this answer in the calculator, so basically you add these two fractions. So you press 1 divided by 6.26 bracket plus bracket 1 divided by 600, and then you do 1 divided of the answer you just got to get your focal length. Okay, so if you didn't know how to get that, that's how you would get that. So you get your 6.2 centimeters here, and that's your excellence grade for getting the correct answer there. Right, so on the diagram below, draw the ray diagram to show how the light from the film reaches the screen. Sorry, what am I doing? So you should know that this area here is our screen, and our lens is represented by our vertical axis. So okay, so now we don't have our object, but we do have our image. So we're gonna use the exact same rules. So the same 3 rules in order to find where our object is. Usually we're going from the object to find the image, but this time all we're doing is reversing the process. So we're going from an image back to the object. Alright, so one important thing to note down, so things that you can identify straight away. You should know that the image has to be real image. Why is the real image? The real image is because the film is projected on the screen, and only the real images can be projected on the screen. So therefore, you know that there are 2 real rays meeting together to form the image on the screen. Alright, so you always go from the top of the image. So you know the image is formed on the screen. So you go from the top of the screen. Okay, that's where image is, and you're gonna start using your rules to identify where your object is. Alright, so I'm going to use two rules. So the first rule I'm going to be using is the ray passing through the center will continue without any deviation. So if I draw a ray here passing right through the center, it will keep going without any deviation. And our second rule we're going to be using is a ray passing through the passing parallel to the horizontal axis will refract through the focal point. But this time we're going to be doing the opposite way. So our ray is going to going back to the focal point, and it's going to when it hits the vertical axis, it's going to refract back 90 degrees. Sorry, it's the other way. So it's going to pass through our focal point onto our vertical axis, and then it's going to refract 90 degrees. And that's how you can locate where the position of your object is. That is where the 2 rays are meeting right now. Sorry. So the 2 rays are meeting at this point here, as you can see. So that's where your image will be. So now you can just draw your final, not image, your object will be. So you can draw your object in. That's where your object is, okay? And you have to note down the nature of the image as well. So the nature of the image, okay, as you can see, it's real. It's inverted. Okay, so why is it inverted? The object was inverted and the actual thing was upright, so it switched polarities. So therefore, it is inverted. Okay, and it's also magnified. The image is bigger than the object. And this question was a merit point. Okay, you get a merit point for correct ray diagram and correct nature of the image. It's a merit point there. Alright, so now we'll move on to question 2. Question 2, refraction. So A says, what is meant by the term refractive index? So refractive index is meant by how optically dense a medium is compared to another. So we have to be in depth with our answers. So we're going to be saying that refractive index refers to how optically dense a medium is. How optically dense a medium is, and how much the light will speed. How much the light will speed up or slow down. And that's basically all you need to write here. And that will get you your chief mark there. Okay, B. A green incident light ray with a wavelength of 453 nanometers travels from air, refractive index of 1, to glass, refractive index of 1.45, at an angle 35 degrees to the normal as shown in the diagram below. Complete the diagram to show the direction of the light ray will bend. Calculate the angle of refraction. Right, so the first thing we're going to do is going to draw our refracted ray. So we've got to note that air, our refractive index is 1.00, and glass, our refractive index is 1.45. Instantly, you can see that we're moving from a less dense medium to a more dense medium, and that can only mean one thing: is that the ray will slow down and bend towards the will bend towards the normal. Okay, so that's the points you got to be noting down here. Okay, really important. Okay, so therefore, when you draw a refractive ray, it has to be bending towards the normal as shown on the screen right now. So it has to be so the angle of incidence has to be bigger than the angle of refraction. And basically that's the direction, okay? And you got to calculate the angle of refraction. So therefore we're going to be using our Snell's law to calculate the angle of refraction. So n1 sine theta 1 equals to n2 sine theta 2. So we're going to note down our n1 is 1 and our sine theta 1 is 35. So 1 sine 35 equals 2. Our n2 is 1.45 and we do not know our sine theta 2. So now we'll have sine 35 divided by 1.45, and we'll find the sine inverse of that. We'll find the sine inverse of sine 35 divided by 1.45, and that will give you your theta 2. If you plug this into a calculator, you should come out, your theta 2 should be coming out to be, theta 2 comes out to be 23.3 degrees. So this angle here is 23.3 degrees. And this question will get you a merit point. For the correct ray diagram drawn and the correct calculation will get you a merit. Alright, moving along. Oh, so I have it on a separate document. Sorry guys, ran out of space. Alright, so a light ray is shone into a prism. The light hits the glass air boundary at an angle of 45 degrees. Despite the prism being completely transparent, light is able to reflect off the glass air boundary as shown. The prism is surrounded by air. Air has a refractive index of 1. By first identifying the physics concept involved, explain why light is able to be reflected off the inside of the prism as shown in the diagram. Alright, so I don't actually have the diagram right now, but if you refer back to your test paper, you should see that the diagram shows the total internal reflection. So the light is going up, it's in the glass, and it's trying to get out of air. However, the angle of incidence is greater than the critical angle, and that means the total internal reflection has occurred, and therefore the light will bounce and reflect internally inside the prism. Alright, so the three main points you have to consider here. First one, so these are very important. So always in the exam, remember these 3 points. Number 1, identify what the physics concept is. Okay, that's total internal reflection. Number 2, you have to state what conditions are required for this to happen. So condition number 1, it's always you have to be moving from a more dense medium to a less dense medium, because that's the only way the light can bend away from the normal. And our second condition is that the angle of incidence must be greater than the critical angle. And then you explain the critical angle is the angle of incidence when the refractive ray refracts 90 degrees to the normal. So that's the main 3 points you have to cover here, okay? So number 1, okay, I go through them one more time. It's very crucial that you remember this. Every year in the exams, this question will come, okay? Well, not every year, but there's like an 80% chance this question will be in the exam. 80 or 90% chance. So it's very important that you keep in mind what the physics concept is, okay? So once more, okay, first thing you have to do, identify the physics theory, total internal reflection. Second of all, think about the conditions. Always moving from a more dense medium to a less dense medium. Third condition, your angle of incidence must always be greater than the critical angle. Alright, so now you know your 3 concepts, and now all you have to do is write it down onto your answer. Alright, so your answer should look something like this, okay? So the theory, so you explain what the theory is. That of total internal reflection. So you can just say bracket TIR, so you can say bracket TIR, so you don't have to keep writing total internal reflection, because that's a big time waster. So you write it, so make sure you write it the first time, so you write it total internal reflection, you write it the first time, and then you put bracket TIR, so the marker knows that you know what total internal reflection is, so you don't have to keep writing out the full word each time, because that's, once again, that's just a time waster, okay? So the theory is that of total internal reflection, okay? You can just describe it a bit more. So you can say, where all the light ray is totally internally reflected. Reflected. Alright, so now that's basically our first bullet point done and dusted. Okay, so now we're gonna go to our conditions. How can this happen? Alright. So we can say the light can only be internally reflected is when we are moving from a more dense medium to a less dense. Okay, so it's good to make a comparison with what you have right now. So right now you have glass moving into air. So you can say bracket, glass is more dense than air. So you say that the glass is more dense than air, and therefore the total internal reflection can happen. So that's our second bullet point down. It's just that it's really simple. Okay, so now we're going on to our third bullet point. So the angle of incidence must always be larger than our critical angle. The angle of incidence, the angle of incidence must always be larger than the angle of than the critical angle. Critical angle. So you can say angle of incidence must be greater than critical angle. So you can give a little description of what the critical angle is, but it's not really necessary. So you can say the critical angle is when the refractive ray. So we can just say the critical angle is when the refracted ray refracts 90 degrees to the normal, and the corresponding angle of incidence is the critical angle. And that's really all you need to get your excellence grade. So you're studying these 3 bullet points, very important bullet points here. And that's all you need to do to get your maximum grade for this question. So, internal reflection and your 2 conditions. Alright, calculate the minimum refractive index of the glass must have in order to... calculate the minimum refractive index that the glass must have in order for the glass to reflect in the way shown in the diagram. So basically, when it refracts in the way in the diagram, it's basically the total internal reflection, and that can only happen when the angle of incidence is greater than the angle of critical angle. Alright, so this time it gives you your angle of incidence, it gives you your it doesn't give you, let me rephrase that. So it gives you your angle of incidence, and it gives you so basically you're just trying to figure out what refractive index is required for the critical angle, and you're saying that the angle has to be larger than that, okay? So I'm going to come on to this page. So let's find out the critical angle, okay? So we're going to use n1 sine theta 1 equals to n2 sine theta 2. Alright, so n1 we don't actually know, that's the glass, okay, we don't know. So we're just going to transfer, so n1 sine, if you look up at your, sorry, I don't actually have the diagram, I apologize once again, but you should look up on your diagram right now, and you should see a sine 45, it should be your angle of incidence, that equals 2, and 2 is 1, sine 90, because we're trying to find the critical angle, and that's when the refractive ray refracts 90 degrees to the normal. So now we just can figure out for m. So sine 90, that equals to 1. So it basically n1 equals to 1 divided by sine 45. And that n1 should come out to be 1.414. Alright, so now that's the refractive index required for 45 degrees to be the critical angle. However, if we increase the n1, the critical angle will decrease. Okay, how can we prove that? Okay, so the QC can be calculated by the sine inverse of n2 over n1, if I'm not mistaken. So n2 is always the same. N2 is always 1. And if our n1 increases, so if our n1 goes up, that means this whole thing will decrease. And if this decreases, then sine of a lower number, so sine inverse of a lower number, that will give us a lower result. So therefore our critical angle will also decrease. So by increasing our n1, we're decreasing the angle of the critical angle, and therefore the total internal reflection can happen. Okay, so now we can just say in order for TIR, our n1 must be greater than 1.414. Alright, and that's all you really need to get your merit grade here. So that's just a merit question, okay? Yeah, it's just a merit question, so that's your side. What am I doing? Okay, so you get your merit grade there, and that's the end of the test. Alright, so I hope you enjoyed this walkthrough video. I hope you understood everything. And if you enjoyed, please slap a like, and I hope to see you all in the next video. Thank you. Bye.